Hi, today we're going to step into the world of cosmology and use our mathematical prowess to determine the temperature of a black hole, or more precisely, determine the temperature of a black hole's event horizon. Now, to carry out this derivation, we're going to rely on something called dimensional analysis. So, in physics, a dimension refers to basically a measurable physical quantity. So, for example, if I want to know how heavy my bicycle is, I would determine its mass. I would measure the mass. If I wanted to know how long it takes me to drive to the cottage, I would measure the time it takes me to get to the cottage. And so there are 7 fundamental dimensions in physics. 4 of them are listed here: mass, time, length, and temperature. And they're denoted by the letters capital M for mass, capital L for length, capital T for time, and theta for temperature. Now there are 3 other dimensions, fundamental dimensions, but we'll be relying on these 4 for our derivation of the temperature of a black hole. Now, what does dimensional analysis set out to do? Well, we use the dimensions of variables in a physical system to deduce the forms of possible relations among those variables. So for example, if we wanted to determine the position of a free-falling object, we might consider quantities such as the time it's been falling for, or the strength of the gravitational field that the object is in, or perhaps a whole bunch of other considerations and other quantities. But the trick with dimensional analysis is to really hone in on the most fundamental quantities that we think are really specific or fundamental to the problem. So for us, we're going to rely on 3 main factors of a black hole. The first is the area of its event horizon. And we can think of the event horizon of a black hole as that sort of imaginary boundary around the black hole that if you pass through it, you can never come back. You can never escape. The second is the entropy of a black hole. And then the third is the radiation that's emitted from a black hole. Now, in terms of the characteristics of a black hole, we often think of mass, electric charge, and angular momentum as being defining characteristics. But to keep our analysis simplified, we'll ignore the fact that the black hole will have any net electric charge, and we'll ignore the fact that it might be spinning, so it has no angular momentum. So essentially, we're going to be looking at Schwarzschild black holes, meaning that the main characteristic of our black hole is the fact that it just has mass, that it's a massive object. Okay, so where do we start with the derivation of this temperature of a black hole? So let's start with the area of the black hole's event horizon. So what might factor in to what determines the area of the event horizon? Well, as we mentioned, mass is a critical factor. Most black holes are very massive. After all, they are remnants of exploded stars. And so if we have a massive object, then perhaps it takes up a large area. So the more massive the object or black hole, the greater the area of the event horizon. Perhaps even Newton's gravitation constant, or the universal gravitation constant, will be a factor, because after all, we know that black holes severely warp space-time because of the extreme gravity that they generate. And maybe even the speed of light will be important. After all, black holes are so vicious that they don't even allow light to escape. So let's start with those assumptions there, or those sort of educated guesses, that the area of the event horizon might perhaps depend on the mass of the black hole, Newton's gravitation constant, and the speed of light. So for the mass of a black hole, when we measure that physical property, the dimension we're looking at is, well, mass, capital M. But how about the gravitation constants? Well, it's not a time, it's not a length. Well, what is it? Well, from Newton's law of universal gravitation, we know that the force of gravity, F sub g, that is experienced by 2 objects attracting one another is proportional to the product of their masses, call those m1 and m2, and it's inversely proportional to the distance r squared separating those 2 objects. Well, what is the proportionality constant that relates the strength of the force of gravity to this expression m1, m2 over r squared? Well, that is precisely capital G Newton's gravitation constant. Well, what dimensions make up capital G? Well, we can rearrange this equation to determine that. We know that force is measured in units of newtons, but newtons is just a combination of other units. In particular, if we think of Newton's second law, F equals ma, force has units of mass times acceleration. So the units of force is mass times acceleration, and for mass we use kilogram, and for acceleration we use meters per second squared. But of course these are units. We want to know the dimension of the force of gravity. Well, kilograms is just a mass. Meters is just a length. Seconds is just a time. And so the force of gravity has dimensions of mass times length divided by time squared. On the right side of our equation here, we have G times two masses, the product of two masses. So one mass times another mass gives a mass squared. And then we have this R, which is the distance separating the two masses. And that distance is measured in dimensions of L, or length. So we have length squared. So now we'll put square brackets around G, and that indicates that we're looking for the dimension of that quantity. And we can just cross multiply here and isolate the G to determine what its dimensions are. So bringing this L squared up here gives us an L cubed, and dividing this M squared down here cancels one M out in the top, leaving one in the bottom. So we have L cubed divided by M T squared in the bottom. And so this is the dimension of the gravitation constant. So let's make note of that over here. And we'll erase this. Now how about the speed of light? Well, it's in the name. We're looking for a speed. What is the dimension of speed? Well, if we think of particular units that we measure speed in, we might have miles per hour or meters per second. But miles and meters are just lengths, and hours and seconds are just times. So speed has dimensions of a length divided by a time. Okay, perfect. So here's our educated guess that the area of the event horizon depends on these three quantities here: mass, gravitation constant, and speed of light. So now our job is to determine what exactly that relationship is. And what we do is look at the product of these three quantities. And each of these quantities is raised to a particular power, and we have to find the value of those powers. So if we assume that the area of a black hole or its event horizon is proportional to these three quantities, we have the product of the mass times the gravitation constant times the speed of light. And each one of these is raised to a particular power. Our job is to find those powers. Okay, well then, what are the dimensions of area? Well, again, think of how you would measure area in specific units, maybe square feet, square meters, but feet and meters are just lengths. So area is measured in dimensions of length squared. So the dimensions of area are length squared. Here we have mass, and the dimension of mass is, well, just mass. Then we have the gravitation constant. And so here are the dimensions up there. L cubed divided by mass times time squared, all to the power k2. And then the speed of light, speed has dimensions of L over t, all to the power k3. Well, to make our analysis slightly simpler, let's do the following. Let's take what we have in this bracket here and write it as the following, so that we eliminate the fractions and just think of the exponents here written across one line. And same thing here, L times t to the minus 1 to the power k3. Our job again is to find the values of these exponents k1, k2, k3. So we'll equate what we have on the left with what we have on the right side. On the left we have an L squared, but no m's and no t's. On the right hand side we have the following: m to the power k1, L cubed to the power k2, that's L to the power 3k2, m to the power minus 1 to the power k2, that's m to the minus k2, and then t to the power minus 2 to the power k2, that's t to the minus 2 k2. And then we have L to the power k3, and t to the power minus 1 to the power k3 gives us t to the minus k3. But this mass and this mass, these powers, give us m to the power k1 minus k2. These powers of L give us L to the power 3k2 plus k3. And then these powers of t give us t to the power minus 2k2 minus k3. So let's equate exponents on the left and the right. On the left-hand side, for L, our exponent is 2. On the right-hand side, our exponent is 3k2 plus k3. Now, on the left-hand side, for the mass, the exponent we have there is 0. But on the right, the exponent is k1 minus k2. And on the left, for t, time, again, the exponent we have there for t is 0. But on the right, we have negative 2k2 minus k3. So when we solve this system, we obtain the following. K1 and K2 both have a value of 2, and K3 has a value of negative 4. So what does that tell us? It tells us that the area of the event horizon of a black hole is proportional to mass to the power of 2 times the gravitation constant to the power 2 times the speed of light to the power negative 4. So that gives us m squared g squared divided by c to the power 4. Now if you carry out more sophisticated, careful analysis, the proportionality constant here turns out to be 16 pi. So the area of a black hole event horizon is actually given by 16 pi times m squared g squared divided by c to the power 4. Now how we obtain 16 pi, we won't get into that now. Again, that relies on some more sophisticated analysis, but this now is the area of the event horizon for a black hole. So we'll block that off. And now let's go on to the second factor here on the new board. Let's look at the entropy of a black hole. Okay, so we're back. Here's our results from the previous board. Now let's move on to the entropy of a black hole. So what do we mean by entropy? Well, what first comes to mind is often the words disorder or randomness. But what we want to really think about entropy as is the number of microstates or configurations that a system can have. So for example, take the room that you might be in right now. It contains air molecules. Some of them are nitrogen, some of them are oxygen. And there's a lot of configurations or microstates that those particles can be in. For example, if all the nitrogen atoms were placed into one corner and all the oxygen atoms were placed into another corner, that would be a very ordered orientation or configuration. But if we let those molecules intermingle and flit about and get all mixed up pretty randomly, that would be what we call a highly disordered state, a configuration or microstate of the particles that are very random. So in a black hole, when objects fall into it, they don't actually get sucked into the black hole, but the information gets smeared across the event horizon. And so that information that's all scattered about will be in some sort of microstate or configuration. Could be ordered, could be disordered, depending on how the particles are configured. Now in thermodynamics, we say the following. That for an incremental change of entropy, ds, of a system, it's equal to the incremental change in heat that might be added to or taken away from the system divided by its temperature. And we also know from the famous physicist Boltzmann that the entropy of a system is given by the Boltzmann constant K times the natural logarithm of W. And here W is exactly those microstates or number of configurations that a system could have. So here's our proposition. As we just mentioned a moment ago, all the information that falls into a black hole gets smeared across its event horizon, but that horizon has a particular area. So perhaps the entropy of a black hole is dependent on the area. So let's make that proposition. Well, if the entropy of a black hole is proportional to its event horizon area, then we can say that the entropy equals some proportionality constant times A. But this proportionality constant B, well, how is it built up? From what quantities is it made? Well, first of all, if we look at this equation right here, entropy equals heat divided by temperature, we can determine the dimensions of entropy. The dimensions of S is going to be nothing more than, well, we measure heat in joules, and temperature has dimensions of theta. That's a fundamental dimension. Well, when we think about energy, we might think about things like work. And work is just a force dotted with displacement. Now again, force has dimensions of mass times length divided by time squared, and displacement has dimensions of length. So that means energy, or heat, has dimensions of mass times length squared divided by time squared. And then we're dividing by temperature. So the dimensions of entropy are nothing more than mL squared divided by theta times T squared. So if that's the case, what are the dimensions of this proportionality constant B over here? Well, we have the dimensions here for S on the left. B, we don't know what the dimensions are. And again, area just has dimensions of length squared. So dividing L squared here on the left just leaves us with dimensions of B as m over theta T squared. But through what more fundamental quantities might B be comprised of? Well, again, let's think about this in an educated manner. Again, we're talking about black holes. Black holes have an extreme gravity. They don't let light even escape. So perhaps the gravitation constant, capital G, will be important, and the speed of light, little c, will be important. Is there anything else? Well, perhaps this Boltzmann constant K will come into play. After all, this is a fundamental property or parameter that relates the entropy of a system to the number of microstates that it has. Okay, so we have that. And then why don't we propose that because we're dealing with entropy, we're dealing with microstates or configurations of particles. But particles are governed by the laws of quantum mechanics. So what's a fundamental parameter in quantum mechanics? Maybe Planck's constant h, or even h bar. Well, let's go with that then. Let's consider the gravitation constant g, the speed of light c, the Boltzmann constant little k, and h bar, the reduced Planck constant. If that's the case, then This proportionality constant B will be proportional to the product of these quantities, each to some power. Let's call those again maybe K1, K2, K3, and K4. Well, our job now is to determine these values. Now, you might say, well, how about the mass of the black hole? Maybe that's something that's very important, or maybe some other quantity. Well, it turns out that if we try to introduce another variable here, we're going to have an underdetermined system of equations. So let's just stick with this for now. Well, we know then that the dimensions of B are mass divided by temperature times time squared. G, we already determined what those dimensions are from earlier. That's L cubed divided by mass times time squared. That's all to the power K1. Speed here, the speed of light, has dimensions of length divided by time to the power K2. The Boltzmann constant, K, well, that actually just has the same dimensions as S, since the logarithm of a number is dimensionless. So what are the dimensions of S? We have that up here, ml squared divided by theta t squared. So those are the same dimensions for K. All to the power K3 times h bar. Well, without getting into too much detail, the dimensions of this are ml squared divided by t. So now our job is to do exactly what we did earlier. We'll have to eventually equate all the exponents on the left-hand side of these variables or dimensions with what we have on the right-hand side. So let's do that. Okay, so here we are now, let's continue. Over here we have the following. The masses, on the left we have an exponent of 1. On the right-hand side we have a negative K1, a K3, and a K4. On the left-hand side for theta, we have an exponent of negative 1. On the right-hand side, we have an exponent of negative K3. On the left-hand side, for t, time, we have an exponent of negative 2. And on the right, we have negative 2K1, negative K2, negative 2K3, and negative K4. And then for L, length, we have no exponents. 3K1 on the right, plus K2, plus 2K3, plus 2K4. So solving this system of equations gives us the following. K1 equals negative 1, K2 equals 3, K3 equals 1, and K4 equals negative 1. So from the previous board, when we had B is proportional to G to the power K1, C to the power K2, K to the power K3, and H bar to the power K4, this tells us then that B is proportional to G to the power negative 1, C to the power 3, K to the power 1, and H bar to the power minus 1. But since entropy equals B times the event horizon area, that implies that the entropy is proportional to this times area. But it turns out again, if you do a really rigorous and sophisticated analysis, that S equals C cubed K divided by 4G H bar times area. So there's an extra factor of 1/4 here. But the area of the event horizon is nothing more than what we have still written up there. So that tells us that the entropy of a black hole is nothing more than 4 pi gm squared K divided by H bar C. Okay, perfect. So let's add that to the list of our results. Now let's come back and focus on the radiation emitted from the black hole itself. Okay, so here we are now back at our final board. Our summary so far of results is here. So for the radiation emitted from a black hole, let's look at the physics involved there. From the first law of thermodynamics, we know that the change in the internal energy of a system is equal to the change in the heat that's added to or extracted from the system plus the work done to or by the object. Well, for our case, let's assume that the black hole is isolated in space and it's not doing any work on its surroundings. So the work will be 0. But we also remember from the previous board that ds equals dq divided by t. But now let's also say that if the total energy content of the black hole is given by E equals mc squared, then we can combine these relationships into the following. First of all, ds equals dq, or in other words, dE over t. But E is nothing more than mc squared. Since C is a constant, we can extract that out in front. And so we have ds equals c squared times dm over t. So if we put this all together then, we can say that the black hole temperature is just T equals c squared dm by ds. But we have an expression for S over here in terms of the black hole mass. So why don't we write the following? That the black hole temperature is c squared times the inverse of ds by dm. Because we can go right up here now and determine S prime, the derivative of S with respect to m. So that just gives us eight pi gmk divided by h bar c. Therefore, plugging that result in, we get T equals c squared times ds by dm inverse. So this result, we'll just flip it around. And now we can take c squared times c to give us c cubed. And there we have it. We've come to what we've wanted to derive all along. This is the temperature of a black hole. T equals h bar c cubed divided by 8 pi g mk. So I hope you enjoyed that derivation. Thanks for watching. Please subscribe to my channel, give this video a like, and consider supporting me on Patreon.